in the Windows subsystem, Linux may have some problem where you can give CP just -R and directory name instead of CP-RF, which works in Ubuntu or Linux. Okay. So it depends on operating system and what type of terminal you are using. So CPR directory name, that should work for you. Okay. So that should copy actually all the files also. And then, so that is one comment. I will not answer any specific application questions here because that's not within the scope of this session. Right. So yeah, some of the questions like what kind of basic knowledge you need and etc. I will try to give a broad overview in some time as we start in 2 minutes. Okay, what is current number? It is already used. Last time is a keyword. It's already used. Thanks, Laxman A, for answering most of the questions. And yeah, what else? Okay, so please do tell us about sources for learning other OpenFOAM solvers. Okay, so it depends. I will again show you the tutorial link for different other solvers, which, like, for example, multi-phase flows, right? So what solvers can you use to simulate a multi-phase flow? So I will go to the folder link and show you those folders again so that you can start with those tutorials. Just copy those tutorial files into your run directory or wherever you feel it's suitable. Like for me, I've just pasted in desktop, and you can start with understanding these files, what it is written, and run the simulation and try to understand it. So yes, that is one point. So one is about some basic knowledge that you need, and other different OpenFOAM solvers. I would show two things. I will just make a note of it. Okay. I don't know what is there in the financial tutorial. I have not explored it because it is beyond my expertise. Okay. Is there any uses other than CFD? As I said, you can use OpenFOAM for solid mechanics problems, purely solid mechanics problems, and also coupled problems like coupled with fluid, coupled with solid, coupled with electromagnetism, etc., etc. You can use it for solving porous structures, etc., etc. Is OpenFOAM efficient for cardiovascular simulation? Again, I won't answer these questions. Yes, it can be used, but it's a specific application. You need to either develop your own solver or use appropriate solvers that is useful for your project. OpenFOAM can be used for many different problems. Now, my area of expertise is fluid dynamics, aerodynamics, fluid structure interaction. And I have no shame in accepting the fact that I only know OpenFOAM for those particular areas, and to a bit extent of multi-phase flows. And all of these areas have, of course, turbulence associated with it. But beyond my knowledge, it's a very vast repository of code, which one can explore to the point of their interest, and they can build their own expertise, right? Okay, so can you also exporting geometry of any of the softwares? I am actually sorry that within the time that I am left with, which is basically 40 minutes, I cannot show you that example. I don't think so, because I have many more things to after this, an example where you export a geometry, which is very easy. So I am just telling you as a fact that suppose you make your geometry in Fluent, ANSYS Fluent, and what you have to do is that you get the export the geometry as the format of Fluent, ANSYS Fluent, and then you use a command to convert it to the polymesh directory, which is, for example, Fluent mesh to foam. Okay. So I'm just writing here if somebody is interested, but I won't be able to cover it today. So this is the comment that you use to convert ANSYS Fluent mesh into a polymesh directory. All right. Again, particle flow, droplet drawing. Yes, you can. I have seen people have done those kind of problem. I have no expertise in that, so I won't comment on that. Two-phase heat transfer. Yes, you can use it. Right. Again, so for ICM CFD, there are like, it's a bit of basically syntax, right? So I don't remember all of this syntax for all of the different meshes to import, but it is available online. I can share you the link again with the material for different kind of uh, other type of third-party meshing softwares. What are the comments to convert them to polymesh directory? But it's pretty straightforward. It's just one line of keyword to convert it to a polymesh directory. All right. Which is better, Salome or Snappy Hex Mesh? 100% Salome, because Snappy Hex Mesh is good again if you really try to control it in every way with boundary layer meshes and so on and so forth. And it's good for a very complex geometry, but where you don't need much accuracy. It can be a crude simulation. Snappy Hex Mesh is okay. But if you really go to the accuracy level of, comparing with some experiment, you need really a good mesh. And a good mesh is the first tick off to get the best solution out of the CFD, right? Otherwise, you can get anything out of CFD, and instead of being computational fluid dynamics, it will become a colorful fluid dynamics. So, and which will not be validated with your experiment. So once you get the computational results, to believe it, to know that they are accurate, you need a very rigorous validation with respect to either other references in a statistical sense or with some experiments. Now, Salome, I would really suggest you to learn GMSH and Salome to actually start learning how to make better meshes. All right. Okay. Okay, so now that we have passed 10 minutes, let me continue with the rest of the content that I wanted to show you. And again, I will look into the comments in a bit later. All right. Aditya, should I continue?
Yeah. You can.
Okay, so coming back to my slides where I stopped, I actually, again, I have showed you that, and I think which is very, very important, that before using OpenFOAM, you need to source this basrc file, which I showed that it is located in the etc folder of your installation directory. Or you can actually create the alias, and this is the way to create the alias in your system basrc. So what you need to do is, in your system basrc, you have to just add this kind of line. Here I have shown it for OpenFOAM 7 just for an example, but it will be open for me in my computer. It is written as OpenFOAM 2306 as source my folder user leave OpenFOAM 2306 etc basrc, right? Which I just showed in the terminal. Now, some more important thing about environmental variable. Now, OpenFOAM has many environmental variable which are actually quite useful once you activate the OpenFOAM. Like, as I already showed that the foam comment, FOAM, leads you directly to the installation folder. All right. Now, WM project directory is actually also the same, leads you to the installation directory, whereas WM project user directory leads you to the run directory, which is supposed to be a different directory or different folder with your name and the version of OpenFOAM that is created. And as a best practice of CFD, we normally copy all the tutorial files to our user directory and then run it. Now, similarly, I have shown this TUT foam tutorials it runs. If you go type just SRC, it directs you to the source code files where all the source code is located, and so on and so forth. All right. And now, just to see this environmental variable, if you, this is a useful comment in your terminal. If you just give environment vertical line graph foam, it will show all of these environmental variables that is available in OpenFOAM. All right. So now, yeah, and somebody asked me, right, that where is the alias for tutorial TUT is located. This is where it is located. So within the etc folder, you actually have a file called config.sh. All right. And this is again, I mean, I have taken this screenshot some time back. So that time the version was different, for path was different. But for me, again, if you go to the installation directory, which is this, it has a etc folder. Within the etc folder, you have a config.sh. And within the config.sh, all these aliases are written, which we can use. And one of them I have used multiple times is the TUT, which can take you directly to the tutorial folder. All right. Okay. Right. Now, again, which I showed already, it's a useful comment. If you just type this, these slides I will try to share with you. So it's fine, you will get it. So environment, vertical line, graph, then foam. This gives you all the path of where these environmental variables lead you to, which are the folders that are important. Like foam SRC is just located in the SRC folder with the installation file. Similarly, tutorials is located in tutorials, and whatever application, solver, etc., whatever directory is important to you, you can go there, you can see the path and look into what are there in there. Right. So this I have already told you, and I don't want to spend much time here. It's basically there is a difference between WM project directory and WM project user directory. So WM project directory leads you to the installation folder, whereas WM project user directory leads you to the user directory where you run your cases. And I have already explained all this, so there's no need. Just to recap, you have 0 constant system. Within system, you have these files, 0 and constant, you have these files. And these are the different solvers. We have now seen IcoFoam, all right? And we will now try to see another solver, which is PimpleFoam. So there are different solvers even within incompressible flows. And we have now seen initial and boundary condition. And what are the different type of boundary condition? We have seen fixed value, where we need to fix a value to the parameter. We have seen fixed gradient, where we need to actually give a fixed gradient of the parameter, or we have seen how to give 0 gradient. So these are the different types of boundary condition. And now we have seen control dict, we have seen FV schemes, we have seen FV solution. Now let's come back to a bit of OpenFOAM programming, which I won't go into much details, but give you some idea about the fact that you can modify the code. And I will try to show you the source code of IcoFoam at least, so that you know that what is written within the IcoFoam solver that you have just run and visualized the results, right? So as I said, that OpenFOAM is a written in C++. It is an object-oriented programming. And instead of the std namespace, which is generally becomes the namespace for C++ code, in case of OpenFOAM, we have FOAM. And within this namespace, we have multiple classes and objects and functions which are defined within this namespace, right? Basically, this namespace is a kind of class. And within that, we have multiple objects as functions, which is defined within this FOAM namespace. Now, for example, dimension set, its class is tensor. It's a tensor, and any variable in OpenFOAM, as I said, has a proper dimension set. And you, as you have seen, that the pressure has the dimension of pressure divided by density, velocity as the dimension of velocity, something like that. And any C++ code will have a main code file, which is .c, and we'll have a header file, which is code.h, which we'll see in a moment, right? Now, what are the primary objects defined in OpenFOAM? We can categorize these objects or the major functions defined in OpenFOAM based on space and time, like polymass, fvmass, time. These are like related to mass and the time variable. We have field algebra. We have different boundary conditions objects like fp patch field and maybe different derived boundary conditions. Finite volume discretization. This I will explain in more detail, which is FVC and which is FVM. Then we have matrix. Related to matrix, there are different objects: LDU matrix, FV matrix, linear solvers, etc., etc. Right? And there is also a very well-defined object registry in the OpenFOAM code. And those who doesn't know C++ properly, it's a bit difficult to understand at this moment, but just get the idea that, of the fact that how the data is read and written in OpenFOAM. It follows an appropriate object registry, and basically the top level object registry is the time class. So basically, for example, if there is a file transport properties, which you have seen, which is within the constant folder, how is it read in OpenFOAM when the code runs, right? So those are defined by the object registry of OpenFOAM. Now, for example, if you go to the input output code of OpenFOAM and see, it will be written as this file name transport properties will be read at every runtime. Runtime is the main object here of constant. I mean, every runtime it will be read, and input output object is must read. It will be it will be read every time step, but it will not be written. That means that transport properties is not overwritten at every time step. All right. So it remains constant, and that is the reason it is in the constant folder. So similarly, so basically it is just to know that there is a specified object registry which follows to read and write the data, and it is associated with the time class. Now, this is important, where we define what is FVM and what is FVC. All right. Now, when you have read about partial differential equations, you know that the terms in the partial differential equation, some of them are explicit and some of them are implicit. All right. And so basically in OpenFOAM, there is two main classes defined. One is FVM, which is finite volume method, and all the functions within this would handle the implicit terms, whereas FVC is finite volume calculus, and all the functions defined within this class actually handles the explicit terms. For example, in this equation, FVM, as I said, ddt function, which solves the time derivative, has a rho implicit as an implicit function within this, right? Within the derivative, there is a rho. So we cannot explicitly take the rho out of the derivative. And that's why we have to solve it within FVM, which is a finite volume method, right? And which handles the FV matrix object. Now, whereas grad P, as you said, as you can see that within gradient of pressure, we do not have anything implicit, right? So it is quite explicit, and that's why it belongs to the class of FVC, right? And here are some of the examples which will go to FVC. Like if it is ddt of just A, it will be FVC. But since it's rho comma A, because rho is implicit, it is FVM, something like that. All right. So hopefully you get some idea about what is FVC and FVM in your equation. And ultimately, when this is also something I already mentioned, when we basically ultimately ended up discretizing a partial differential equation, it leads us to a set of linear equations in the form of AX equal to B. And we need some linear solvers to solve that. And the matrix class is FV matrix, and which is derived, which is a subclass of LDU matrix, and which is a general matrix class. And we have multiple linear solvers as a function defined within that. Like I have already shown you PCG, which is preconditioned conjugate gradient. We have P by CG, preconditioned biconjugate gradient, etc. And there are multiple which you can read up in your CFD knowledge and choose which one is the best for your problem, basically. Now, as I have already shown you that we have used something called preconditioner, right? Preconditioned conjugate gradient. So what is this preconditioner? Now, a preconditioned iterative solver solves a problem like AX equal to B by multiplying a preconditioner in the both the sides. Now, what is the use of it? The use of it is preconditioner leads to a faster propagation of information through the computational mesh. So this is purely from a numerical perspective. We do it just to increase the efficiency of and reduce the computational cost of the linear solvers. And this can be done in many ways: left preconditioning, right preconditioning, etc., etc. And there are multiple preconditioners available, and you have already seen this DIC, which is diagonally incomplete Cholesky. All right. Okay. So going ahead, let's see the source code of IcoFoam, and then I will again take up some of your questions and discuss whatever overall we discussed, and we will visualize another simulation of flow around a cylinder quickly, which I will not describe all the files because I've already explained to them. I will show them to you and then basically show you the visualization. How does it look? Right. So can anybody tell me at the end of this, where should we find the IcoFoam source code? That's a kind of check whether you are following or not. Where do you think the source code of IcoFoam is located? And this is a bit a tricky question. Okay. Right. Everybody writes SRC, which is wrong. One person, I think Surveys has given the correct answer, which is application, and Christopher, because applications has the solver folder, as I have shown you. And within the solver folder, according to the category of different problems, different solvers are located. So let us look into it, and let us look into the source code of it. All right. So let me try to share my terminal again. Hopefully this is the terminal. Right. So let's, yep. Okay. So we are now within the folder cavity, which is in my desktop, right? So we have to go back to the installation folder. And what do we do to go to installation folder? Can you write in the chat box? Which command do we use to go back to the installation folder? Foam, provided the fact that my OpenFOAM is activated by sourcing the BASRC, which is done already. So the right answer is foam, and we go to the installation folder, OpenFOAM 2306, and then we go to applications and solvers. All right, and we see what are the solvers are there. And we can see that we have different solvers which are categorized. We will go to incompressible, and we will see there are multiple solvers. We will go into the icofoam solver just to see what is there located. And we see, as expected, we have the source code in the form of the main code icofoam.c, and along with the header file createfields.h. And we have a make folder, which is just to compile this code, which is used to compile this code. Okay, and we will see what is there. So now, for example, first look into the header file. So whenever you see a C++ file, all the definitions normally are included in the header file. So for us also, we have a createfields.h file. Let's look into it, what is written there. All right. So it writes info, which is nothing but a display comment that reading transport properties and line. And then this is the object registry of input output dictionary. It is reading the transport properties. And how does it read? It reads IO object transport properties runtime constant. So every runtime it reads it, and it is linked to the mesh. That means it reads this value for all the grid points of the mesh. Okay. And then IO object, it writes must read if modified and no write. Okay. So basically, by default, it will read it. And it shows this must read. That means, I mean, don't go into the complication of modification, but basically, if it is must read, means it will read at every time step, and it will not write it, overwrite it every time step. That is the important thing, because it is in the constant folder. Okay. Now, next it reads dimension scalar new, which is, where is it located? Can somebody tell in the chat? Where is new located? Where is this new written? What is new? New is kinematic viscosity. Okay. So in constant, there is a file transport properties. In the transport properties file, we write new, the value of new, which is kinematic viscosity, right? And it gives the dimension of viscosity, and it is written in the transport properties, which is, it is written here actually. Then it reads pressure, right? So pressure is a scalar field. As you all know that pressure is scalar, and it is defined as a volume scalar field because, okay, here another questions. So basically, I have already told you that we showed you a two-dimensional simulation of lead-driven cavity. Now, why is pressure defined as volume scalar field as and not surface scalar field? Why is it volume scalar field? That's because by default in OpenFOAM, all the simulations are 3D, all right? And we restrict the solution into the third direction by applying the empty boundary condition, all right? And that's why all the variables, scalar or vector, they are defined as volume vectors, all right? That's important to know. So depending on your boundary condition, you can restrict it to a 2D simulations, but by default, it's a 3D simulations. Now, what is the difference between the transport property and P file? The difference is that must read is the same, but the auto write. Okay. So previously it was no write, but in this case, it is auto write. That means basically the value of P is changing at every time step. And we need to record the value of P at every time step, how it is changing, right? And then basically it reads U. Similarly, it is must read, auto write. And Then it includes another header file, which is somewhere else. It's create_phi.h, which basically another header file, which has the definition of phi, which is nothing but is the velocity flux. All right. So that's enough for your basic understanding. So now that we know the header file, let us now see the main code, which is icofoam.c. Okay. Okay. So instead of create field, we see the icofoam.c. So congratulations that some of you, at least for the first time, are coming to the source code of an Navier-Stokes solver, which is, I think, interesting. If at least some of you have never seen this source code of OpenFOAM, then I think that's where the success of this session lies. Just to show you the fact that it is different from commercial softwares and it is not a black box. You can look into it, understand all the lines of it, can modify it, and create your own solvers. Right. So you can see here, starting from the code. So it is generally the structured as a C++ code. And as at the start, you have to include all the header files. Here I have, it's basically, it's included the basic header files, which is FV CFD, which is finite volume CFD, where all the definitions related to CFD and finite volume are already written previously. And then piezo control, because we are using the piezo scheme, we have to include another header file. And then this is just a note. And then basically it includes many other different header files which are needed for this solver to run. Then important stuff is here, which you must understand. Okay. So this part. Now, what it is written here. Now, this actually writes the momentum equation, all right, which is U equation. Now, as I've already told that this time derivative, it is by default included into FVM, but here there is nothing else. So we could also do it FVC, but it is generically written. So if sometime you want to include some implicit parameter, then it will go to FVM. And again, this divergence, there is a phi parameter, so it's FVM. Laplacian also, there is a new parameter which is implicit, that's why it's FVM. And then we have a moment predictor and predictor corrector loops for the piezo. And then we solve the U equation, and the right-hand side is grad P. So this is nothing but the incompressible Navier-Stokes equation written in a high-level programming language, right? Then the piezo loop continues, and we calculate these terms, which comes from the derivations of the piezo algorithm. So I think if we organize masterclass or multiple session in the next session, then we will explain this line by line with the derivations and with the CFD equations, right? So in 2 hours, we don't have really time to go into that. So then we adjust this flux to maintain the equilibrium, maintain the continuity and volume, flow volume corrections, etc., etc. And then, yeah, so then basically then we every runtime write the results and etc. So basically this is the code. Of course, every line you don't understand at this stage, but the take-home message from this session would be to understand the governing equation, which you are basically solving, and how to modify it. And how to modify it, I will quickly show you. But as an example, I don't have time to basically show you, but I can direct you to one of my YouTube channel videos, which shows how to create a my Laplacian flow solvers from the scratch by taking this code, modifying it, compiling it. So I will give that link to you in the material. So if you are interested, you can just see that YouTube video and can do it yourself. All right. All right. Now that we have seen icofoam.c, and we will just see how to make your new solver, just introduction to it. And then if we have a future more detailed session for a couple of days, we can discuss this in very detail starting from here, right? So I will stop my sharing here and try to share my presentation again. All right, so what's the time? Yeah, so at this stage, now only one last thing I want to show you is that, yeah, so I didn't show you here, but in the make folder, you have these files and options, the two files, which we need to modify if we want to compile the code. And this is where I mostly stop with the kind of introduction is that how do you compile the source code? So of course, if you want to modify this icofoam and add, suppose you want to add the temperature variable to it, right? So you want to modify the governing equation and also solve for temperature with the appropriate initial and boundary condition. Then what you have to do is you have to copy this icofoam folder, the whole folder from the solver to your run directory. Okay. Which where you will have this .c file, .header file, and the make file, which has files and options. And then you have to modify the C code as you wanted. And then you have to change the names in these files to compile it. And you have to use the command wmake. Okay. So I think let us do it in terminal, which will be better. So let's stop sharing this and okay. So I'm back to my terminal and let us first see if we can go to my run folder, right? So if I give my run folder, where does it go? There is yeah, so it doesn't go to my run folder, but it's an interesting thing. It doesn't go because I have not created the run folder yet, but it goes to the path where my user directory is, and where it is in my home ADF BOSC OpenFOAM. There is a folder called BOSC-2306, right? And which is supposed to contain a run folder which is not created. That's why it's not going. So is it clear that the path of the installation directory and the user directory is different? And let's look into it in a bit more systematic way. So let me reset it. So I am now in a terminal somewhere within icofoam. I want to go back to my installation directory. I do FOAM and I am in the installation directory. Now I want to go to my user directory. And as I showed you that the environmental variable is WM project user directory, right? And I'm back to another folder, which is located exactly in a different folder. The folder is named as my username with version 2306. And this is my user directory where I want to copy the source code and then modify and then compile. Okay, so this is the place where you create your new solvers. And to do that, to make it more systematic thing, I create by mkdir a folder called src. Okay, so within my user directory, I have now a src folder within which I will copy my source code, right? So to copy it, I will copy the folder which is located, forgotten the path, probably let's try. So WM project directory, which is my installation directory, then application. Yep, it is coming. So applications is the name. And then basically I have solvers. Okay, right? Then within that I have incompressible, right? And then within that I have icofoam. Okay, so that is my folder that I want to copy. So this path is something you need to remember. So icofoam, right? And I want to copy here within the SRC folder, right? So let us copy quickly. Yep. Now, if I see I have icofoam, and now what the first point is that I will rename it. So move icofoam folder to, let's say, my icofoam. Okay. So now it is moved. Now inside that, I have now basically the files icofoam.c. That also I have to actually rename, because we cannot create a new solver with the same name. So let's move icofoam.c into my icofoam.capital C. All right. Now, if I go to the make folder, I see that there is two options, these files and options. And now within the files, what I need to change is that I have to change the name of the solver, first of all. So I have changed it to my icofoam.c. And here I need to change foam user app bin, because I'm doing it within my user directory. And what will be the executable? My executable will also change to my icofoam instead of icofoam. So this is, imagine, now I'm saving it. So imagine that I have made some modifications, right? And then I want to rename it, and then I want to compile it. So to compile it, hopefully it will work. It may show some error in some cases. So wclean. Okay, so I have to go back again. So wclean, and then we use wmake, and it's compiling. Okay. So I didn't do any modification to the code, but however, I have basically renamed it and compiling it again as a new solver. Now imagine that you have done all the modifications that you have done, then you have compiled, voila, you have your new compiled solver, my icofoam.c. Is it clear? Right. So that is how you go to the source code and then modify it and then make your own solver according to your need. And here I would basically close the main conceptual thing of this session with a visualization of flow past cylinder. And then I will take 10 minutes to answer your questions. Okay. So let's reset it and go back to okay, where am I? Go back. Okay, so I'm here. I have to go to desktop. Okay, I have to go to cylinder today. So all right. So this is a simulation, which is a flow past cylinder, and the mesing has been done in Snappy using Snappy Hex Mesh. However, in the interest of time, I don't have time to show you how to mesh it using Snappy Hex Mesh, which is also kind of falls into the intermediate learning, which is a bit involved. So once you know how to do properly with block mesh, then you move to Snappy Hex Mesh. But I want to end this session with a visualization showing you the mesh which has been created by Snappy Hex Mesh and what can we observe as a physics as a vortex setting. To do that, basically, I create the results dot foam and I open it using paraview results.foam. And once the paraview window opens, I will stop share and share the paraview window. Okay, you can see it. Similarly, we basically untick the skip 0, apply, and at 0, okay, we start from why it's not going to 0. All right, maybe we have deleted the 0 folder. So it's the folder is available only for 0.5. And if you see the maze first, this is the maze that you created using SnappyHexMesh. Now, the caution here is why SnappyHexMesh is not very much preferred is because of these cells. So how SnappyHexMesh works is that it first takes a STL file, which is the geometry file of the body. Then it cuts the cells within that, depending on the controls that you give to the SnappyHexMesh, how many layers and what is the maximum non-orthogonality and skewness you want, etc., etc. And as a fact, you see that SnappyHexMesh is not that good in getting you a proper clean mesh, right? So that is where I would prefer GMSH or Salome, or if possible using block mesh to make a clean mesh. So here I have already calculated the vorticity. So if you go back and try to see how the vorticity will look like as a surface vorticity Z. And this is the option somebody asked. This, you can see this option is the option to give you the option to change the range, right? Change range of the color map. So -10 to 10, if I give, right? All right, now you can see that my color bar has changed to -10 to 10, and then you can see how the, okay, so it's not very much visible. I have to change the scale again. I make it -3 to 3. Okay, it's depending on, it's still not very much visible. So -1 to 1. It depends on what is the value of vorticity you have got, right? Now it's better, visible better. And then if we play the simulation, you can see the vorticity that gets set behind a cylinder. Now, exactly the setting is same. This has the 0, constant, and system folder. This is in the tutorial folder anyway, but the solver is different. Instead of IcoFoam, I have used here PimpleFoam. And PimpleFoam is a transient Navier-Stokes solver, which gives you the option to also include turbulence models as you need. So apart from that, all the settings that I've explained for cavity are almost similar. Of course, the schemes and the solvers are different because the physics is different here in terms of the cavity. And that is where you need your fundamental knowledge of computational fluid dynamics, which you gain through your courses or books, textbooks. All right. So with that, I close my part of the thing, and I will try to answer some of the questions. Aditya, are you there?
Yeah, tell me. Yeah.
Can you please moderate the questions and tell me some interesting questions that in 10 minutes we can discuss?
So if you see here, what is a mesh type file? Is OpenFOAM suitable?
So the
Yeah.
maze type file is, I don't understand what is that. So the geometry is stl.stl, okay? And the SnappyHexMesh considers that geometry file and creates the mesh in the polymesh folder. Okay, so the mesh is still located in the polymesh folder within the constant.
Yeah. So what we will do, we will take some 3 to 4 questions. So those who are having questions, technical questions only, there will be no more general questions. If you have some questions, so just raise your hand. Maybe Vignesh will unmute you, so we can have a discussion and we can wind up the meeting, wind up the session now. Then. So I'm sharing the survey form as well. Just you try to fill the survey form, so you'll come to know, okay, what are the things required in the future session, and it will be helpful for us to redesign the upcoming sessions. So I'm sharing the link. You can just put your comments. Okay. So just if anybody is having a doubt, they can raise the question. We can take 3 to 4 questions, and then we can wind up the session. No, no, you can raise your hand. You don't have to unmute yourself. If I say unmute, then everybody will unmute. It will be a problem. So you can raise your hand. Yeah, yeah, yeah. Yeah, Vignesh, can you unmute Himanshu? Yeah, Himanshu, now
Can
you
you
can.
hear me, sir?
Yeah,
Yes.
yeah, yeah.
Yes, Himanshu.
So I have one doubt regarding the Navier-Stokes equation, the momentum equation, which you showed. So
Yeah.
there was within divergence phi into u, phi times u. So can you explain what is that phi and why we are using FVM, since OpenFOAM only, in OpenFOAM we can only write divergence as FVC. So how are we using FVM
Yes,
as
exactly.
divergence
So
and what
this
is
is
phi?
what I tried to discuss, the difference between FVC and FVM. Now,
Yes.
FVM is used for implicit calculations, right? As you have this phi comma the variable, the phi is a scalar here. It can be anything, any scalar. I mean, depending on the problem, it's generically as defined as phi. I mean, in my equations, it can be temperature, it can be anything that any scalar you want to define. Now, because this is implicitly mentioned in the equation, because this cannot come out explicitly outside the divergence, that's why we have to use FVM. Am I correct? Because I don't remember that equation now, but from your idea, that is my answer. And if there is nothing as such, just the variable is there, then we can use FVC, which is explicit. Next. Well, Fluent seems to be easier than OpenFOAM. Of course, yes. If you don't want to think, don't want to know what you are solving, just click buttons. Please don't come to OpenFOAM. Keep using Fluent. That's my suggestion. Yes, next question, please.
Yeah, Chitrak is there. Let me unmute him. I think it is not unmuting. Okay, then might be the case because the support person he went. Yeah.
All right, I will just read some questions from the chat.
Yeah, I think Chitrak is unmuted.
Okay, Chitrak.
Am I audible?
Yes.
So I have working on a problem like that and seeking some suggestion about that. If it is possible in OpenFOAM.
Chitrak, we'll focus with some general topic here so that
Yeah,
others
you can
will not.
don't hesitate to email me about your problem. If it falls under my expertise, I will try to answer it. But as I said, this session doesn't really discuss about particular problems. It's just a beginner session. So please feel free to email me. Okay. Thank you.
Okay, then we can finish. We can complete the session. So first, I would like to thank Dr. Chandan for very informative. From the basic onwards, he covered a lot of things in least possible time. So basically, the motive of this session is to get a basic understanding about the OpenFOAM. So those who are not aware of OpenFOAM, so they can have a basic ideas on what exactly the OpenFOAM is all about. We do understand the time is very short. We will not able to address all your queries in the session, but we'll try to have some other sessions in future where we can have a long sessions, including TAs. They'll help you out with some case studies or with some examples, so we can have some hands-on. So I hope this session might be useful for your basic understanding. Now you can just try to practice the things. Dr. Chandan will share the PPT along with his YouTube channel. So you can have some idea from there so that in case if we in future we are having the session, so the basic things might be not an issue for you. So you can start the thing smoothly and we can have a discussion in different domains as well because we have a lot of time. We will design in such a way so that we can have a lot of time and we can have a networking session also for different domains of fluid mechanics, heat transfer. So people will come up there, they'll discuss their problems, they'll discuss. So it will give you the opportunity for collaboration as well. So we'll think about it and we'll redesign the session. So I already shared the feedback form to you all. Just try to fill the feedback so that we can come to know about like how the session is all about, and what are the improvements we need to do in for the session. So one more time, I would like to thank Dr. Chandan for such a big session of 3 hours, nearly 3 hours. I think.
Thanks, Aditya. And I really hope that the effort that I put in at least encourage some of you to learn OpenFOAM. And that was the motive of this session, not to teach you everything, but just to make you excited about it. And as Aditya mentioned, of course, in 3 hours or 2.5 hours, I tried to cover starting from what is OpenFOAM to compiling your new solver, and which is a lot of information to digest, I understand. So I hope at least you remember the basic structures and methodology, but in the future sessions, we will take all of this in small things and we will actually make you understand in more depth. That's what I can say.
Yeah.
And thank you all of you for all of your interest and joining the session. Thank you very much.
Yeah. Thank you all, and have a great Sunday. Okay, bye.
Bye-bye.